So as always, we're going to start off with a review. So this should look extremely familiar by now. So we talked about generating measurable signal. We put our patient into the scanner in the presence of kind of the resting magnetic field, and we induce some magnetization. We turn on an RF pulse, and that pushes that magnetization into the transverse plane, which is something that we can measure. So this happens at some frequency, right? And we said that because of the principle of resonance, that we get efficient energy transfer between our RF pulse and the spins in the patient that are at the same frequency, right? And so whatever frequency our RF is set at, if it matches the frequency of the spins in the patient, then we bump those spins into the transverse plane, and that's our signal that we can measure. And we said that this is something that we do multiple times, right? And what we're actually doing is we're turning on the RF pulse, and then we're turning it off, and we're watching what happens. And so, that's what we've diagrammed here. We put the patient in the scanner, we turn the RF pulse on, we get our transverse magnetization, and then we turn it off, and it decays back until there's no transverse magnetization. And then we graft it over on the side here, right? We turn the RF pulse on, we get transverse magnetization, which is a signal that we can actually measure, and our longitudinal decays. And then when we turn our RF pulse off, they go back to a resting state. But they do this at different rates, right? And so the next thing that we talked about was, the fact that it takes different amounts of time for tissues to kind of get rid of that energy that we've put into the system. We can use that to generate contrast, right, in our signal. And we talked about, how there are a couple of different mechanisms through which this occurs. Transverse magnetization occurs through, or transverse magnetization decay, so up here, occurs via spin-spin interactions, right? Interactions between protons. And that's described by something called T2. And then we talked about longitudinal relaxation or longitudinal decay. And that was via something called spin lattice interactions, which was between the protons and just other things in the sample. And there's something called T1, right, that we used to describe that. So that was the basis for contrast. How do we tell signal apart if it's right next to each other? This is just a little bit more on that, right? We talked about how, this is kind of like our idealized T2 contrast, right? But in actuality, what we're getting is something like this, where there's some degree of T1 contrast also encoded in our signal, right? This should look familiar. I'm not going to go through it all again, but what we actually see a lot of the time is something that looks like this right here on the bottom right, where there's some degree of both the T2 information as well as the T1 information that's in the signal. And by adjusting our TE when we measure our signal, and by adjusting the TR, which is how frequently do we turn that RF pulse back on again and repeat the whole thing, by adjusting these parameters, we can choose whether or not we want to weight our signal, weight our image more towards T1 or more towards T2. This is kind of the last thing that we talked about. We introduced this idea of free induction decay. And this wasn't really anything new. This is just, again, visualizing what we've been talking about this whole time, right? So on the left here, we're graphing basically what is happening to the signal over time. So the y-axis is kind of our signal amplitude, and the x-axis is time. And this is just a measure of what is happening with our signal. And so you'll see that, on the very far left, we apply our 90-degree RF pulse, right? And we excite a bunch of spins, so we get transverse magnetization. And then over time, that decays, right? And we talked about why that is, why that decays back, and how it does that through the different mechanisms. We talked about how, loss of this signal is, explained in part by this loss of phase coherence here on the bottom, right? The spins are getting more and more out of phase over time, and so you have less and less signal to measure. And how this initial one was called T2 star, right? This is like what we actually measure. And we talked about how, if you apply another RF pulse, this time you do a 180 and you just kind of flip this all over, you can actually reform your signal. And for whatever reason, when you reform this signal, it's a cleaner signal. And it does away with a lot of the inhomogeneities related to paramagnetic contaminants and, artifact and what have you that were affecting this signal. When you hit it with this 180 pulse and you reform and create an echo, this echo is a lot cleaner. And this is kind of more along the lines of our idealized T2 curve, right? So this is really what we end up measuring almost all the time. Okay, so this should look pretty familiar. And again, we touched on, how been getting signal from everywhere, right? We'd been exciting the entire patient. The patient was placed into a uniform magnetic field, and therefore all the spins in the patient had the same frequency as well, equally uniform. And so when we apply our RF pulse at that frequency, we're exciting all the spins in the patient, right? And so we end up exciting a volume of spins that look like this, and our final image is just, monochrome, just one color. And okay, so that's not ideal. So the next step, right? This is what we talked about last time, was to apply a gradient along the long axis of this patient. And the purpose of that gradient was to create a difference from one end of the patient to the other in the strength of the gradient magnetic field. And the reason we do this is because as we're creating a difference in the strength of the field from the patient's toes to the patient's head, we're also inducing a difference in the frequency of spins from the patient's toes to the patient's head, right? Because those things are proportional, the field strength and the frequency. And the reason we do this is because then when we apply our RF pulse, only the spins in the patient that have the same frequency as the RF pulse are going to be excited. And so that's the basis for slice selection. So this gradient that we applied along the long axis of the patient here, we call that our slice select gradient. Okay. That's something that we'll be turning on along with the RF pulse in order to select our slice. So we got here, we generated signal that we could actually measure, and we figured out how to select down to a slice. Okay, the next question is, how do we go from selecting a slice to making an image, right? And so that's what we're going to talk about today. And this is just summarizing kind of the ideas of slice selection again, right? So just review a couple of concepts here. If we wanted to change what slice we're exciting, one way that we can do that is we can just change kind of the parameters of our RF pulse, right? We've set our RF pulse to excite frequencies between +1 and -1, right? And that corresponds to this location on the patient. So these spins will be excited. But if we changed our RF pulse to excite spins between -5 and -6, well, that's going to excite spins here along the patient, right? So we'd get kind of more lower extremity as opposed to abdomen. So by changing the RF pulse, you change where along that slice select gradient you are. And as a result, you change which slice you're going to excite along the length of the patient. Okay. And then looking over here on the right, we talked about a couple different ways that we can change slice thickness. So one way to change slice thickness is to change the strength of the slice select gradient, right? So here, this is a steeper gradient. And down here we have a shallower gradient, right? This is shallower than this. And the effect of that, if with a steeper gradient, if you set your range for your RF to be between +1 and -1, well, that's going to occur over a smaller distance, right? Because you have a steeper gradient, you have a greater rate of change from the patient's foot to the patient's head. And so as a result, that you're going to that range of frequencies is going to occur over a smaller part of the patient. So your slice is going to be thinner. On the other hand, if your gradient isn't particularly strong and it's very weak or it's very shallow, well, you're going to have a scenario that's closer to the resting state before we even applied this gradient, right? When we didn't apply a gradient at all, you excited the whole patient. So the weaker your slice-select gradient is, the more you're going to kind of approach that scenario, and so your slice is going to be thicker. The other way to do this was to change transmit bandwidth over here, right? And to review, all the transmit bandwidth means is the range of frequencies that you apply your RF pulse over, right? We said RF pulse, you can't apply RF pulse at 5 and 5 only, right? That it's actually a range, and you can make that range wider or narrower. Okay, so here our range is, we have our transmit bandwidth is 2, right? Because we're transmitting between +1 and -1, and we get this thick of a slice. If we broaden our transmit bandwidth and we make our bandwidth 6, right, between +3 and -3, well, you've just excited a greater range of frequencies in the patient. And so it should be intuitive at that point that you're exciting more frequencies in the patient, you're going to have a thicker slice. Okay, new stuff. So this is actually nothing new. Again, I'm just mapping out here everything we've talked about up until now. Okay, so let's walk through this. This is over time, and I probably should have put a time marker at the bottom to illustrate that, but this is over time. Okay, so we have our RF pulse that we talked about, right? And at some time, we apply a 90-degree RF pulse, and that's illustrated by this curve here. Okay, and we said that when we do that, when we apply our RF pulse, anytime we do that, we also have to apply that slice select gradient, which is this second line here, this blue box, right? It's the combination of applying that slice select gradient and the RF pulse at whatever range we pick, like here. It's that combination that allows us to pick a slice. So this RF pulse and slice select gradient together, this is what picks your slice. Okay, so they're applied together at the same time here. And when you do this, you start to generate signal here, right? So now we start to get signal. Okay. At some time, we apply our 180-degree RF pulse. And that does what, right? We talked about that. That flips everything. So instead of diverging and losing signal, now we're reforming our signal, right? We're putting things back into phase. That's what we're showing here. So at some time, after that signal is kind of died down a bit, we hit it with our 180 pulse and our slice select gradient again, right? So we're only applying this 180 pulse to our slice. And what happens? Our signal starts to reform. And this curve that it reforms at, coming up and then coming down, this is more of our idealized T2. And this whole thing is called an echo, right? This is how we generate our echo. So this is what we're interested in listening to out here. So this is everything that we've talked about up until this point. This is nothing new. Okay, I'm just mapping it out, what's happening over time, so you can start to see how this whole sequence of events is fitting together. You'll notice that every time that we apply the RF pulse, we're applying the slice select gradient at the same time, whether it's 90 degrees or 180 degrees. All right. So this lecture is talking about spatial encoding, right? We've talked about contrast, right? We talked about selecting a slice. Now we got to figure out where is the signal coming from in that slice. So the way we do this is kind of the same way that we selected a slice. We just apply more gradients. Okay. So we selected a slice by applying a gradient along the long axis of the patient, right? We could say we applied it in the z-axis. So our phase encoding and our frequency encoding gradients, these are just gradients that we apply along kind of the x and y dimensions then. This is our slice thickness here. So frequency encoding is just something that we apply kind of along one side of our slice, and phase encoding gradient is what we apply kind of, usually we show it along the vertical dimension of our slice. And remember that, all of this can be changed any which way depending on if you're doing, axial, coronal, sagittal slices, whatever you want to do. But this is just kind of the convention of how it's shown. Okay. Usually frequency encoding is shown along the bottom, phase encoding is shown along the side. Doesn't really matter. But it's gonna work in a similar way to our slice select gradient in that you're creating a change from one side of the slice to the other. So if we look over here on the right then, when we apply a phase encoding gradient, this is what it looks like with that phase encoding gradient off. Okay. When it's turned on, down here at the bottom, the gradient is weak, so you don't see much change. But as the gradient gets stronger from one side of the slice to the other, you see everything start to deflect more, right? And then when you turn it off again, that stays there. Now the signal has been encoded like that. So that information is still there when you turn it off. Frequency encoding, you're applying it along this axis, right? So it looks like this. And so spins, on one side of your slice are going to be spinning with a lower frequency. And as you move across your slice, from one side to the other, like this, they're going to be spinning faster. They're going to have a higher frequency of spin. So this is how you encode spatial information into your slice. And so you can imagine it looks something like this, okay? Where you have phase encoding along one side, and you have frequency encoding along the other. And if you apply both of these gradients, you can imagine that all of the little voxels in your slice are going to have a unique combination of phase and frequency, right? They're going to have a unique address, as it says over here, a phase address and a frequency address. And that corresponds to a pixel on your image. You're applying these gradients perpendicular to each other, and as a result, you're encoding your signal with information that will eventually allow us to localize each of these voxels and create an image with it. So if we plot this out, we're just adding to the diagram that I showed earlier. Again, this is happening over time. So once again, we have our RF at the top, and at some point in time, we apply our RF pulse, our 90-degree RF pulse, right? And when we do that, we apply the slice select gradient at the same time, which is this second line. And this is our slice selection. So now we've excited all the spins in the slice. And we've generated some signal, which I could have drawn down here, but we don't really care about it, right? We're only interested in the echo. So this is our slice select. Now after that, we hit it with a phase encoding gradient. This has been shown to occur depending on which diagrams you look at. Sometimes it'll be drawn before the 180 pulse. Sometimes it'll be drawn out here after. I'm sure there's a great reason for it, and it probably depends on what special type of sequence you're trying to create. But for the purpose of our discussion, it doesn't matter. Okay, so if you see this over here in a book or something, don't worry about it. Just know that the first thing you do is you select your slice, right? After you select your slice, you can kind of do whatever you want. So the first thing that we do here is we apply our phase encoding gradient. And we just talked about what that is. And then at some time, we apply a 180-degree RF pulse along with our slice select gradient again, so we're only working on the slice. We generate our echo with that. And then when we go to read this signal out, we apply our frequency encoding gradient. So at this point, when we're reading out our signal, we've applied our phase encoding and our frequency encoding gradients. Okay? So this signal should have information about phase and frequency in there, encoded in there. A couple more things that are on this diagram. We talked about how, the time from when we apply that 90-degree RF pulse to when we measure our signal, that's our time to echo, right? Again, this is nothing new. This is, that's this. This is when you apply your RF pulse here on the left, and this is when you listen to the signal, your TE, okay? That's the time difference there. That's all we're talking about here. Nothing different. Time from when you apply your RF pulse to when you measure your signal, okay? So that's our TE. Another thing that they'll throw out there is when do you apply your 180-degree RF pulse? And you just apply it at 1/2 of TE. So whenever you're going to measure your echo, at the midpoint of that time, you're going to apply your 180 pulse. Okay. So are we done? Is that it? Did we just encode phase and frequency in our image and now that's it? Of course not. Okay, so why not? Okay, let's look at our diagram again. Same diagram. This signal that we measure, this echo, okay, where's it coming from? Where's this signal coming from? And the answer, as I've given you here, is it's coming from the whole slice. Okay, it's coming from the whole slice that we've excited. Okay, that's kind of a problem, right? Remember I showed you this image? So this is kind of a lie in the sense that it's showing you that if you apply phase and frequency here, that you can just kind of almost kind of like a map say, well, we apply phase and we apply frequency, and so if we know the phase and the frequency, we can just directly convert this into our image, right? No, that's not what happens. It's not a direct conversion. You can't signal from one particular voxel in the patient does not get directly converted into an image pixel. And why is that? Because anytime that you measure signal coming out of the patient, you're measuring signal from the entire slice that you've excited. And I think this is like the most difficult, or like the least intuitive thing about this whole process. But the point is that you physically cannot record signal from a single voxel in the slice, okay? You can't, when we have our patient in the scanner here, you can't go and say, oh, well, I only want to apply my RF pulse to like this one little box here, and I only want to measure signal coming from that one little box. You can't do that. So when we apply our gradients, you can't just say, oh, I only want to look at this one voxel here. I only want to look at this one voxel here. And we're going to measure the phase and we're going to measure the frequency of the signal in that one voxel, and then we're going to plot it on our image. You can't do that because you're exciting the whole slice at a time. Okay. Anytime that we measure signal, anytime that we talked about measuring signal here, that signal is coming from the whole slice that you've excited. Okay, it's just a jumbled mess of all the different signals that are coming from all the different spins in that slice. Now we've encoded information in that slice, okay? There is phase information and frequency information encoded in that slice for sure. But we can't directly convert that into an image because we're still, when we measure our signal, we're still measuring the summation, okay, the composite signal of all of this. So there's phase and frequency information encoded in this slice, but when we measure it, it's still just one big signal. Okay, so that's kind of a problem, right? So we've got a situation again. I'll just restate this. We have a situation where we selected our slice, right? We applied our RF pulse with our slice select gradient. We encoded spatial information into our slice, right? With our phase encoding and our frequency encoding gradients. But when we record our signal, we still get signal from the whole slice all mixed together. Okay, so what do we do? So the solution is more data and math. So you may have heard of something called a Fourier Transform, which is scary and looks like this stuff. Basically, what a Fourier Transform is it's like a mathematical technique, okay, that allows you to convert data. And that's all we're going to say about it. But practically speaking, what it allows us to do, what it allows the computer to do, not us, because we're not good at math. What the Fourier transform allows the computer to do is deconstruct our signal. So it allows us to deconstruct the signal that we acquire from the slice and separate it out into different waveforms of different frequency. And you can see that kind of diagrammed here. So when we acquire our signal, and go back again, here, right, our echo, because it's coming from the whole slice, it actually looks like this. Okay, it's just a jumbled mess. It's got a bunch. I mean, there's no kind of rhyme or reason to this signal here, right? Because it's a composite. It's a composite of the whole slice. And what the Fourier transform basically does is it does a bunch of math. The computer does a bunch of math, and it can actually deconstruct this signal and separate it out like this. And so you can see here it's separating it out, different frequencies. And you can imagine that if you plotted those frequencies, well, you could line them up in the order that they are here, and you could start to figure out where those were coming from in space. Okay. So Fourier transform, why do we use it? Because the computer can deconstruct our messy signal that's coming from one slice and give us something usable. But this last line here is critical, okay? In order for it to decode the signal, it needs more data, okay? We can't just run this sequence one time and give it enough data to go on. And I'll show you what I mean. So let's go back to our diagram. Same diagram again, right? I'm just going to repeat myself over and over so that this stuff sticks and makes sense. We've got our 90-degree RF pulse and our slice select gradient. We turn them on at the same time when we select our slice. We turn on our phase encoding gradient and eventually our frequency encoding gradient. And by turning these on, we encode our slice with spatial information, right, in the phase encoding and the frequency encoding directions. Okay. At some time, which is, at some time half TE, we apply our 180-degree RF pulse and our slice select gradient to refocus our signal, regenerate it, and then at TE, we measure our signal, our messy, complex signal. So when the computer measures this signal, what it's doing is this, okay? It's just plotting what is the signal strength, or what is the signal amplitude over time, okay? So if you were to plot what this signal looks like over time, it might look something like this, right? At the very beginning, there's not much signal, so it's black. Over time, as that signal starts to build up, you get more and more signal, right? Until here, which is at time TE, right? This is the midpoint of the echo. This is where you have the most signal. Okay, so that's nice and bright. And then it starts to dephase again, right, and decay. And so the signal gets darker and darker and darker and darker. So this is just a representation of what our signal looks like over time, as the computer is saying, okay, how strong is this signal, and plugging it in here. Now you can tell the computer, or you can tell the machine, hey, I want you to sample more frequently. Okay, I want you to, instead of the 17 boxes that we have here, let's do this 256 times. Okay, well, okay, you would be able to get a much better idea of what your signal actually looks like the more that you sample. Okay. Here, if you were going to try to reconstruct what the signal looks like with only kind of a few time points, it's going to be a little bit more rudimentary. You're not going to have as accurate of a signal. Okay. But conceptually, what's happening here is when the computer is measuring the signal, okay, it's just plotting, okay, how strong is that signal over time, okay? So it looks like this. So we run our sequence, and we get something that looks like this. And remember, this is not what does our picture look like, right? This is just how strong is the signal that we're recording over time as we're measuring here. Remember how I said we need more data, right? So there's phase and there's frequency information in our slice that we've embedded in our slice by turning on those gradients. So the information is there, but running this one time is not going to give the computer enough information to decode everything. Okay, there's reasons why, and we're not going to get into them because it doesn't matter. Okay, just know that running this one time is not enough. What we actually have to do is we have to run this sequence that we talked about multiple times to get enough data for the computer to be able to deconstruct that messy signal into something that makes sense. Okay, so we run this our sequence, which we call a spin echo sequence. We run this multiple times, and the only thing that we're changing every time that we're doing it is the strength of our phase encoding gradient, this guy here. Okay, so we do the same thing again and again and again. Every time, just add a different phase encoding gradient. And that's kind of what I've diagrammed here. You know, this in the middle, and this is just convention, is kind of like, you know, baseline phase gradient strength. Okay, so this is like how strong is our phase encoding gradient to start. And so that was this right here, right? And so we plot that over time like this. Okay. Now we make that phase encoding gradient a little stronger. Okay. And we plot it over time again. And then we repeat the process again, this time with an even stronger gradient. And we repeat the process again with an even stronger gradient. Each time, what does our signal look like over time? What's it doing over time? And each one of these rows, you can see it's kind of doing the same thing. It's gradually increasing to a maximum in the middle, and then it's getting smaller again, right? And that's just what we would expect. That's what our signal is doing over time, right? And then we make the gradient, you know, a little weaker, right? Or a little stronger in the opposite direction might be a better way to say it. And we plot that down here, and then we make it a little stronger in the opposite direction, and then a little stronger again in the opposite direction, and we plot what happens. Now notice that as we make our phase encoding gradient stronger and stronger and stronger, what's happening to our signal? It's becoming weaker. Now why is that? Why are these rows out here with these stronger phase encoding gradients, why do they have less signal? Okay, the answer is because if we look at our phase diagram again, right? What's happening? If you have a stronger magnetic field, you're going to dephase your spins faster. Okay? So you're going to lose signal faster. In a stronger magnetic field, this curve is going to drop down quicker because these things are dephasing. Okay, so if your phase encoding gradient is stronger, you're basically just distorting your signal faster. Okay, so as a result, when you plot this out, if you have a stronger phase encoding gradient, your signal is just going to be less overall because you're dephasing the spins faster. Okay, that's why these rows look different from one to the next. And this is important. Okay, we said the computer needs more data to be able to run that Fourier transform. And this is how we give it more data. We do the same thing over and over again, but we just tweak the phase encoding gradient each time. It's kind of like the difference between taking a picture of a three-dimensional object from one view. And that gives you some sense maybe of what that object is like. But if you wanted to really know what that object looks like and create a model of it, you would want to take pictures from multiple different angles, right? And then kind of by combining all of those pictures from different angles, you would be able to arrive at kind of, okay, what does this thing look like in three-dimensional space? Does that make sense? That's kind of what we're doing here. So we're repeating our sequence a bunch of times. Each time, we're just changing the strength of our phase encoding gradient. And then the computer is recording that signal over time. So this should look pretty familiar to some of you, right? What is this? What did we just create? This is K-space. Okay. This is all that K-space is. K-space is literally just the information where your computer is plotting. Your MRI, is recording how much signal you're getting and then plotting it over time. Okay? And doing it at all these different strengths of the phase encoding gradient. So it's the same thing here. This is K-space. This is like, for each one of these rows, they used a different strength of the phase encoding gradient, right? And then this is what our signal is doing over time, and it's getting stronger and then it's getting weaker. So this is K-space. Okay, this is just all of the information that we're giving the computer so it can run the Fourier transform and decode the signal. And if you plotted, if you made like a three-dimensional model of it, why would you? I don't know. But it might look something like this. Okay. All right. So this is all of the signal that we've obtained after we run our sequence multiple times, each time at a slightly different strength of the phase encoding gradient, right? So this K-space just represents kind of all of that information. And now we have enough to give this over to our computer. It runs a two-dimensional, or an inverse two-dimensional Fourier transform, does a bunch of math on all of this, and it gives us our image. Okay, now we actually have an image to work with. So let's kind of summarize what we talked about here. So this is our spin echo sequence. And spin echo sequence just means this is the series of steps that we use to generate our echo and encode it with phase and frequency information, right? So we select our slice with our RF pulse and our slice selection gradient, right? We encode our slice with spatial information by applying a phase encoding gradient and a frequency encoding gradient, right? And those are applied along, the x and the y axis of the slice, perpendicular to each other, right? And then when we apply our frequency encoding gradient, that's also when we read our signal at this time TE. And when we read our signal, when the computer reads signal, what it's doing is it's saying, okay, what's the signal at this time? Okay, let's make a note of that. What's the signal at this time? Okay, make a note of that. What's the signal at the next time point? Make a note of that. And it's plotting how strong that signal is over time. Okay, and it looks like one of these rows. And that fills a line in K-space. So if you hear that term thrown around, that's all that means. Filling a line in K-space just means running the sequence one time and recording the signal over time. And we said that because when we record this signal, the signal is coming from everywhere, that now we actually have to repeat this whole thing, our spin echo sequence. We have to repeat this again using a different phase encoding gradient strength. And we do that a bunch of different times. And what that does is it generates basically a bunch of different looks at the data for the computer. And we record those. and eventually it looks like this. And now we've recorded enough information that now the computer has what it needs to run the Fourier transform and generate our image. Okay. I'm just going to make a couple of comments here, pull a couple of things together. So this is what we just talked about. You'll notice here that when we run this one time, our spin echo sequence, the amount of time it takes to run this from our 90-degree pulse and our slice left gradient through until we repeat it again, that's our TR. That's our time to repetition. So TR is how long do you wait before running your sequence again? Okay. That's the same TR that we talked about before. That's this TR up here. It's the time between applying your RF pulse initially and then applying it again. And why do we apply it again? Well, we apply it again because we need to run the whole sequence again. We need to run the whole sequence again enough times to fill all these lines in K-space to give our computer enough information so that now it can run the Fourier transform and decode all of this and make an image that makes sense. Okay, so that's TR, that's time to repetition, right? This is TE, right? That's the time from when we apply our 90-degree pulse and select our slice to when we get our echo, to the midpoint of that echo. And this is when we read the signal. Okay, so TR and TE, again, just shown in the context of what's happening with our signal generation. Okay. A couple other things to note. Again, remember, when we apply our 90-degree pulse, RF pulse, or our 180, we're applying a slice left gradient at the same time. Okay, so these kind of go hand in hand. The other thing that we touched on is the fact that the frequency encoding gradient is always applied when you read the signal. So this will also be called, this guy right here will also be called your readout gradient. Okay, it means the same thing. Readout and frequency gradient mean the same thing. It's just called readout because it's applied when you read out the signal. There's this idea of receiver bandwidth. And what receiver bandwidth is it's the number of these boxes, basically. It's how many times did we sample our signal, okay, over this time period here. And remember we said you could sample this 256 times, right? That would be a larger receiver bandwidth. Okay, and if you did that, you would be able to, your Fourier transform would eventually be able to deconstruct a broader range of frequencies. So it's generally a good thing. There's some trade-offs, which we're not going to get into right now and you can read about, but basically, receiver bandwidth just means how many times are you sampling your signal here to fill one line of K-space. All right. So that's this side of K-space. This side of K-space is phase encoding steps, right? This is how many times are you changing your phase encoding gradient and running the whole sequence again. So the number of rows in K-space, this is phase encoding steps. How many times are you repeating this whole process? Okay, so it's called number, these are your phase encoding steps. And then there's this idea of number of excitations. And the number of excitations is basically, again, how many times you're going to run this whole process. How many times you're going to do the whole thing over again, and why might you do that? Well, let's say you wanted to improve your signal to noise ratio. You wanted to get more signal. Well, a good way to get more signal is to just do the whole thing over again, and then to use kind of the signal that you're getting from both runs of this whole thing. You're going to have more total signal for the computer to work with, right? It's going to improve your signal to noise ratio. The trade-off is, as you can imagine, that doing this all over again is going to require time. So this is the equation that's thrown around and that you'll read and see again. And that scan time, this is an important concept, right? Because scan time is money, and scan time is proportional to your TR, how long it takes to do this one sequence, right? To fill one line, times the number of phase encoding steps, which is basically, okay, times how many times are you running that sequence, each time at a different phase encoding gradient strength, right? Times how many times are you repeating this whole thing and doing it again. Okay. So the whole time it takes for you to do your scan is dependent on how long each it takes to run a sequence, times how many times you're running that sequence, times how many times you're doing all of that. Okay. So that's what this equation means. And remember, we talked about receiver bandwidth here, but we talked about another bandwidth, right? And that was transmit bandwidth. That's not the same thing. They're both called bandwidths, but they're not the same thing. Remember, transmit bandwidth was this. It was what range of frequencies are you applying your RF pulse? What range of frequencies are you transmitting your RF pulse at? And that determined slice thickness, remember? That's this. This is different. This is a different bandwidth. This is now, instead of transmit, this is receiver. This is what range of frequencies can you detect when you're measuring your signal? And we said that, well, you can detect a greater range of frequencies if you measure this more frequently. So you can make changes to this process to do different things to your images. And maybe we'll talk about that next time. But this is kind of the core of it, right? This is the basic premise that is going to be so important to understand before you start understanding, okay, now what's a fast spin echo, what's a inversion recovery, what's any of the other sequences. Okay, this is key. This is the same general sequence of what's happening here is common to all of them.